Swayam Prabha. Digital India. Educated India.
See, we are still looking at this, this classification theorem for space curves, and I was trying to tell you the importance of the fact that the Frenet-Serret differential equations, you look at them as differential equations for the Frenet-Serret frame, then they are first order linear, okay, and that is what allows you to get a solution on a whole interval, okay. In general, if you solve a system of differential equations on an interval, you will get only a solution around a subinterval for each point chosen. You cannot expect that solution to extend to the whole interval. So it is because these equations are linear in nature, linear homogeneous first order. That is why you are able to get a solution on the whole interval, and this is a technical thing. Okay, so the linearity of the Frenet-Serret differential equation is very important. But what you should notice is that if you take the Frenet-Serret differential equation as differential equations for the curve, then it is no longer linear and first order homogeneous, it becomes third order, because it involves curvature, which is a second order term, and torsion, which is a third order term. Okay, so now I just wanted to give this this point of view. You see, if you have, so the idea is you have one independent variable x on an open interval AB, okay, and you have several dependent variables, n dependent variables, which depend on that one independent variable. Okay, then what happens is that you write a linear homogeneous first order system of differential equations in this form, where you write the derivatives of the dependent variables as a column, and that is equal to a coefficient matrix which involves only the independent variable. So these are only functions of x, and then on the right side you have the dependent variables themselves. Okay, so this is a matrix differential equation, and it is this is the type of equation that you have for the Frenet-Serret differential equation. And how do you see that? So what is happening in this case? So we have to see, the point is that when we write it like this, we are writing it for our convenience, but it is not written in a very ideal way. So to understand that, what you must understand is that, you see, the way you're writing this equation, the objects are kind of not of the same species. So for example, you see this guy on the left side, this guy is actually it has there are three, I've written three terms, and each f dot g dot h dot, mind you, they are column vectors. Okay, so actually this is actually, if you look at it like that, you see this fs, okay, is it's a column vector. So basically this is actually f1s, f2s, and f3s. So it's a column. Okay, and if you write fs dot, this is going to be f1s dot, f2s dot, f3s dot. Okay, so what you must understand is, on this side, this is actually, if you write it as scalars, okay, scalar functions, then each of the f's have three components, mind you, because we are in 3 space. Okay, so you see this actually becomes a column containing 9 scalar functions. All right, so the correct way to write it is, you see, so if I just see it like this, you see it is a 3 so I should write 3 rows, one column, and the point is that each row is actually a column. Okay, each row is actually a column, 3 vector. So actually it is, if you look at it like this, this side is actually, it is f1 dot s, f2 dot s, f3 dot s, okay. That is this. Then you have, g1 dot s, g2 dot s, g3 dot s, okay. And this is the second one, and then the third one is h1 dot s, where of course dot refers to d by ds, okay. So h2 dot s and h3 dot s. See, this is the object on the left side, okay, if you write it as scalar functions. And this, so and on the right side, if you look at it, see again this guy here, this is again a 3 row 1 column, where each row is actually a column 3 vector. So this is also, if you write it as scalar functions, it is those 9 functions, okay. So without the dots. So on the right side, see this fellow will become simply, what I'll get is I'll get simply f1s, f2s, f3s, okay. And so let me write this. F1 of s, this is what this will become, and then I'll get g1s, g2s, g3s, okay, and I will get h1s, h2s, h3s, okay. And so this is, you see, this is 9 by 1, 9 rows 1 column. This is also 9 rows 1 column, and you see this fellow is a very special, it's a different species. This is actually a 3 by 3 scalar matrix, because the terms there are actually scalar functions, okay. So you see, actually this is a 3 by 3, a scalar matrix. The coefficients are scalar functions. So you see, it's the way you have written it is actually, it's quite funny. It's not kind of, it's for our convenience, we understand that this is first row, f dot s is first row first column. So what you do is you take this first row and multiply by this first column. But the point is that the first row that you are taking from the Frenet-Serret matrix is a scalar row, and the first column you are taking is a vector column, okay. It's actually it is a column of column vectors, okay. It's kind of so you see, it's not written in a nice way, but for our convenience we are writing it. So if you actually write it correctly, how does this become? See, actually if you write it correctly, what happens is that you will have to replace the Frenet-Serret matrices. All the 0 matrices should be replaced by 0 3 by 3 0 matrix, and all the scalar functions should be replaced by scalar function times the identity 3 by 3 matrix. So the correct way to write this is, I should write here 0 3 by 3 and phi of s times I3, okay, identity 3 by 3, and then I'll get a 0 3 by 3. So this is how I should actually write it. So minus phi s identity 3 by 3, then 0 3 by 3, and then I'll get psi s into identity 3 by 3, okay, and again you'll get 0 3 by 3 minus psi s minus psi of s, minus psi of s identity 3 by 3, and then I'll get a 0 3 by 3, okay. And what is happening is actually, it's block multiplication. You see, it is this 3 by 1 is actually, see, you're only so how should I say that? So you see, you multiply these 3, there are 3 by 1 blocks, okay, and the first 3 by 1 block is gotten by multiplying this with this, okay, which essentially amounts to multiplying phi with these 3 functions, because the other 2 are 0, okay. So if you write it like this, this is the nice way to write it, and this is a 9 by 9 matrix, okay. And what you must appreciate now is that, you see, now what is happening, you see, s is the independent variable, and S is varying over this open interval AB. Okay, what are the dependent variables? F1, F2, F3, G1, G2, G3, H1, H2, H3. There are 9 dependent variables. So so let me write that. So there are actually 9 dependent variables. So F1, F2, F3, G1, G2, G3, and H1, H2, H3 are the 9 dependent variables. They are dependent variables on the independent, they depend on the independent variable S. So they are 9 functions. And this is the situation in which you are applying the theorem that this differential equation can be solved for a solution. So the solution is actually these, there are 9 functions like this, okay, and you group them into 3 to get 3 vector functions, 3 column vector functions, which we call as, you know, F, G and H. So this guy here is your F dot, and this guy here is your G dot, and this guy here is your H dot. Okay, and this here is your F, this here is your G, and this here is your H. Okay, that's how it is written. All right. So what you must understand is that you are getting 9 functions, and so the point is, because this is a linear system, you can solve this for these 9 functions. Okay, and you can get a solution on the whole interval. That's very, very important. Okay, and you can give any initial condition. So we give a see, we are trying to find a curve for which, you know, this capital phi and this capital psi, they are respectively the curvature and the torsion functions. So you need to find a curve. If you want a particular curve, then you need to give some initial condition. But you see, these are initial conditions not for the curve actually. These are initial conditions for the Frenet-Serret frame of the curve, because this F, G and H will be the Frenet-Serret frame of the curve. Okay, so you have to give initial conditions for the Frenet-Serret frame of the curve. So that means you have to give a point and a Frenet-Serret frame there. So the initial condition we give is that we take some point S0, and we say that at S0 this F, G, H should be the some fixed orthonormal frame which we take, you know, I, J, K. So you see, so I want to say that F, G, H, there exists a unique solution, you know, F comma G comma H, such that, you know, at S0, F of S0, G of S0, comma H of S0, this is respectively equal to I cap, J cap and K cap, which are the standard right-handed orthonormal frame. Okay, so and there is a unique solution like that. And the important thing is, by the linearity, such a solution exists globally on this open interval AB. This is very, very important. Okay, the point is that if you choose on the interval, if you choose a point and give an initial condition there, you can only find on a sub-interval containing that point a solution in general. That solution need not extend to the whole interval, but because of the linearity it extends. That is a technical point. Okay, now what is the issue? The issue is that see, we are trying to find a curve for which this is a Frenet-Serret frame. Okay, but then this, what we have gotten is a solution of this Frenet-Serret differential equation. But why should the solution of the Frenet-Serret differential equation be a Frenet-Serret frame? Okay, the fact is that you have only said that this solution is a orthonormal frame at a given point. It's a right-handed orthonormal frame at S0. But why is it that for other As, why should that solution be a orthonormal frame, right-handed orthonormal frame? That has to be proved. Once you prove that, then, you know, you can recover the curve, basically by integrating the first member of the Frenet-Serret frame, which is F. F should be the tangent vector, and the unit tangent vector, you integrate it, you should get the curve. Okay, And then it should be a matter of straightforward verification that if you take that curve and calculate its curvature and torsion, you will get for the curvature the function capital phi, and for the torsion you will get the function capital psi. Okay, but therefore the important thing that needs to be verified is why is this solution, why is it a right-handed orthonormal frame at every point, if it is so at only one point, okay, which is given by these initial condition. The answer to that is one way of looking at it is again appeal to the uniqueness of differential equations, okay. And the other way is to write, to make use of the fact that the Frenet-Serret matrix is actually skew symmetric. Okay, so let me tell you the so let me just write this: need to prove, need to show that Fs, Gs, Hs form a right-handed orthonormal frame for every S in AB. You need to show this, okay, and it's not straightforward. All right. Now, so what is the condition that you need to prove? So basically, see what is orthonormality? First of all, you need that you need two things. First of all, you need that these vectors are mutually perpendicular, and they all have length 1. That is one condition. Then for right-handedness, you need that they form a right-handed triad. So in order, F H should be F cross G, if you want. All right. Or if you take the once you have proved it is an orthonormal frame, okay, it can be either left-handed or right-handed. Calculate the determinant. If the determinant is +1, it is right-handed. If the determinant is -1, it is left-handed. All right. So so you see, to show F GH is an orthonormal frame, we have to show, what is it that you have to show? See, F, G, H are, you think of them as column vectors. Okay, F has F1, F2, F3, G has G1, G2, G3, and H has H1, H2, H3. Okay, basically you are trying to say that matrix is orthogonal. What is the condition for a matrix to be orthogonal? The matrix multiplied by its transpose must be the identity matrix. So what you have to show is F is a column, G is a column, H is a column. All right, and if I write like this, this is a 3×3 matrix. Okay, and I should take its transpose. If I take its transpose, it will be transpose of FGH. Okay, and I have to show this times this. By the way, this is the same as transpose F, transpose G, transpose H. Okay, times FGH. Okay, you have to show that this is equal to the identity 3×3 matrix, which is essentially delta Ij, Kronecker delta Ij, right? This is what you have to prove. Now you see, mind you, F is F, G, H are columns, so transpose F, transpose G, transpose H are rows, and I am writing it as 3 rows. Okay, but you see, what is the what does this amount to? See, that is, you have to show, if you write out the the product, you will get transpose F, transpose F, G, transpose F, H. Okay, then transpose G, F, transpose G, G, transpose G, H. Then I will get transpose H, F, transpose H, G, transpose H, H. Okay, so I have to show that this is equal to delta Ij, 3×3 matrix. Okay, but what does this mean? I mean, basically, what is transpose F? Notice that you see transpose F is actually F dot F. Okay, and for that matter transpose V times W, where is just vector multiplication, I mean matrix multiplication. Transpose V, W is just V dot W. Okay, so basically what you are trying to show is F dot F. So this side is just just dot products, F dot F, F dot G, F dot H, G dot F, G dot G, G dot H, H dot F, H dot G, H dot H. You are just trying to show that this is equal to delta Ij. Basically that means that you are trying to show F dot F, G dot G, H dot H, they are all equal to 1. That shows they are all norm 1 vectors. Okay, and all mixed dot products are 0. This F dot G, F dot H, and by the way, this is a symmetric matrix because F dot G is the same as G dot F, and F dot H is the same as H dot F. So it's a symmetric matrix. Okay, so all the other off diagonal terms are all 0. That's what you are trying to show. Okay, so what does this amount to? That is, you are trying to show that, you see, so let me write this. F dot F is equal to G dot G is equal to H dot H. This is 1. And you are trying to show F dot G is equal to G dot H is equal to H dot F is equal to 0. You are trying to show this. Okay. A priori, what you must understand is that F dot F is a function of S. That's the whole point. Remember that your F is F1, F2, F3. Okay. So you see, so if you write it, you will get F dot F will just give you F1 squared plus F2 squared plus F3 squared. Okay, and what you are trying to show is that this, mind you, this is a function of S, right? Because F is a function of S, all the components F1, F2, F3, they are all functions of S, and you are saying that this sum of squares of these 3 functions is always 1. That's what you are trying to show. So you are trying to show, so you see at the end there are these 6 quantities which are actually scalar functions of S. You are trying to show 3 of them are 1 and the other 3 of them are 0. Okay, so you see, and what is given is that this condition does hold. This condition is true at the point S0. At the point S0, this FGH correspond to IJK. So at that point, this condition is valid. Okay, that is, you have to show this given that at S0, okay, the above holds. Namely, so let me write it carefully. Fs0 dot Fs0 is equal to Gs0 dot Gs0 is equal to Hs0 dot Hs0 is equal to 1, and you have Fs0 dot Gs0 is equal to Gs0 dot Hs0 is equal to Hs0 dot Fs0 is equal to 0. Okay, at S0 it is true, but what you are trying to show is that this is happening for all S, not only at S0. Okay, now you see, here again there is something interesting happening. This is again so this can be again reduced to solutions, uniqueness of solutions of a system of differential equations. Okay, and in this case it will be 6 functions, namely these 6 functions, and why that it is reducible to that is because of the Frenet-Serret relations. So you see, basically what am I trying to show? See, these 3 functions f dot f, g dot d, g dot g, h dot h, they are functions of S. I am trying to show they are equal to 1. Further, it is enough to show they are all the constant, and that constant will be fixed at S0 because it will be equal to 1. So I have to show these 3 functions are constant, which is the same as showing that their derivatives are 0. Okay, so you switch to derivatives. Similarly, these 3 f dot g, g dot h, h dot f, they are also 3 functions of S, scalar functions of S. I would like to show they are all 0. Further, it is enough to show that their derivatives are 0, which will imply that they are all constant, and the constant value is fixed at 0 at that point S0. So you see, showing this is equivalent to showing that all these 6 functions, the derivatives are 0. Okay, so it is enough to show d by ds. Okay, so let me write it in kind of matrix form. I'll write it like this: f dot f, f dot g, f dot h, then I'll put g dot g, g dot h, and then I'll put h dot h. It's enough to show that this is just 0 0 0 0 0 0 0 0 0. Okay, mind you, it's a symmetric matrix, so here also actually the truth is here I'll get f dot g again here, and I'll get g dot h here, and I'll get here I'll get f dot h. Okay, but you can forget these three guys because they are repeating here by symmetry. Okay, so basically what I have to do is that I have to show the derivative of this is 0. But the mind you, derivative of this is 0 will tell you that this is a constant matrix. What that constant matrix is, that it is the identity matrix, you will get by plugging in S equal to S naught. That initial condition you have to use. So basically, you have to only show that these 6 quantities, these 6 scalar functions, their derivatives are 0. But what are those derivatives? Okay, that is where the Frenet-Serret equations come. So you see, if you calculate d by ds of f dot f, this is going to be what is the derivative? You will get f dot f plus f dot f dot. Okay, and this is actually dot product is symmetric, so you will get 2f dot f dot. Okay, and please don't confuse the dot in between the in between two things, that is a dot product, and the dot on top is the d by ds. Okay, so don't get confused with those two. You are asking why I mark them? No, I am saying that I need to only show those 6 functions that appear on the diagonal and above the diagonal. I only need to show that they are all 0. Their derivatives are all 0. And I am saying the ones that come below are just by symmetry. Those 3 are the same as reflection across the diagonal. Okay, so the point is that there are only 6 functions, and I have to show that derivatives are 0. But you see, so therefore what is it that you have to prove? Let me bring in the Frenet-Serret here. Okay, look at this equation. So let us write, there are 6 functions, let's write them one by one. So one non-mixed term we will take, d by ds of f dot f, you are getting this. Okay, but you look at the Frenet-Serret. After all, f dot, g dot, h dot are solutions of Frenet-Serret. And so what is they are solutions of what? So f dot, g dot, h dot, this is equal to the Frenet-Serret matrix 0, phi s, 0, minus capital phi s, 0, psi s, psi of s, 0 minus psi of s, 0 times f g h. Okay, see, f g h satisfy this differential equation because they are solutions. So you plug in the f dot value. So this becomes 2f dot. Okay, what is the f dot value? It is 0 into f. So it's phi s times g. So, and this is a dot product, mind you, phi s is a scalar. Okay, so you will get 2 phi s f dot g. Okay. Okay, so you see, so watch this, d by ds of f dot f is scalar times f dot g. Okay, and if you keep writing like this all the 6 terms, you will see that the d by ds of each of those 6 terms are actually linear combinations of those 6 terms. That means these 6 terms d by ds form again a first order linear homogeneous set of differential equations for 6 functions, you see. Okay, so that is the that is the trick. So you see, so similarly, if you write a mixed term f dot g, let us say, and write d by ds of f dot g, what you will get? You will get f dot g plus f dot g dot. Okay, but then now again use the Frenet-Serret relation. So the point is d by ds of f dot g is also linear, in these these three variables. So therefore you get the following thing. What you get is, see, if you write f dot f, so let me write it in order, f dot f, f dot g, f dot h, then g dot g, g dot h, then h dot h, and these six guys, these six functions, d by ds of that is actually a scalar matrix function of S times this the same those six functions themselves. Okay, so you see what has happened now is that you are getting a system of first order homogeneous linear differential equations. Okay, now the independent variable is of course S in AB. How many dependent variables? Now there are 6 dependent variables. And what are those 6 dependent variables? There are these 6. These are the 6 ones. The various dot products. Okay, there are 3 possible vectors, and then you are choosing 2 at a time. Okay, so you get these 6. You get these 6 dot products. Okay, and what is happening is that derivative of these 6 is a scalar function times these. Okay, and of course you can write out what this matrix is. Okay, but let's not worry about it. It's just a scalar matrix, and we are not worried about what that matrix really is. I'm not worried about it. Okay, I want to use the following thing. I want to use the fact that whenever you have a first order linear homogeneous set of differential equations, simultaneous matrix differential equation in so many independent variables and only one independent variable, then any two solutions, there is always a solution on the whole interval, number one. Number two, any two solutions which have the same initial conditions are the same. In other words, if you give initial conditions, the solution is unique. Okay, but there is a very stupid solution to this. Namely, you take f dot f is 1, you take f dot f is 1, g dot g is 1, h dot h is 1. Take the constant function, and then you take f dot g, f dot h, g dot h to be 0. There is a constant solution which satisfies this differential equation. And this solution, okay, also equals that constant solution at S naught. Therefore, it is the constant solution, and we are done. Okay, so you see, that is the beauty of the use of uniqueness of solutions. Okay, so notice that the functions, the constant functions, one, so I'll write, so I'll write it in the same order as I put it there. So so I'll just put it, f dot f is 1, f dot g is 0, f dot h is 0, g dot g is 1, g dot h is 0, h dot h is 1. So take this set of functions. Okay, these constant functions also are a solution. There is see, the point is there is a constant solution. Okay, there is a constant solution, and that constant solution is going to and that constant solution equals this this solution that we have, f dot f, f dot g, f dot h, etc. At S naught they are the same. Therefore, actually it forces, by uniqueness of solutions, that all these f dot f, f dot g, f dot h, they are all going to be equal to those constant values. That means f, g, h is an orthonormal frame. Okay, so and the solutions f dot f, f dot g, so let me write this and the solution, f dot g, f dot h, g dot g, g dot h, and h dot h equals 1 0 0 1 0 1, okay, at s naught. So basically what happens is that you have one solution and there is another solution which equals this at s naught, therefore they are the same. So by uniqueness of the solutions to the ODE, so this ODE is this ODE, okay, so I'll call this ODE as maybe I'll call it a star, this ODE, okay, it's not the Frenet-Serret ODE, this is a different ODE, all right. This basically this is just a translation of the orthonormality of f, g and h which we are trying to get hold of, okay. So of the ODE star, okay, we get f dot f is identically equal to 1, so let me write it like this, f dot f, f dot g, f dot h, g dot g, g dot h, h dot h is identically equal to this 1 0 0 1 0 1, okay. And this implies that this f f g h is an orthonormal frame. So you get that this is an orthonormal frame, all right. Now there is only one more thing that you have to check, that it is right-handed, okay. To check that it is right-handed, see for an orthonormal frame means if you write the frame as a matrix, then it's an orthogonal matrix. The determinant is plus or minus 1. So for this orthonormal frame at every point, you are getting a the value of the determinant is going to be plus or minus 1 at every point. But you see determinant, so the determinant function is defined on that open interval AB and it is taking values in plus minus 1, okay. Mind you, the orthonormal frame, this orthonormal frame is actually C1, because you see you are solving a first order differential equation. The coefficient functions are continuous, okay, and when you integrate the coefficient functions you will get C1 functions. Therefore the solutions to the first order equation will always be C1, okay. So basically in any case, you see the orthonormal frame is continuous, so its determinant will also be continuous, okay. So basically what you are having is from the open interval AB on the real line, you have this determinant function which goes into again the real line, but it takes only two values, either plus 1 or minus 1, and you have a continuous function. See, a continuous function will take a connected set to a connected set, and the open interval a comma b is connected. See, at some point if it takes plus 1 and at some point if it takes minus 1, by the intermediate value somewhere it has to become 0 in between. But it's an orthonormal frame, everywhere it has to take only plus or minus 1, it cannot take any other values. Therefore the only possibility is that throughout it will take plus 1 or throughout it will take minus 1, but at S0 it takes plus 1, therefore it throughout takes plus 1, therefore it is throughout a right-handed frame, okay. So continuity is and topology is used here, right. So let me write that. So you see, note that you see this FGH is continuous in S, okay. In fact actually C1 AB, it is first continuously differentiable, okay. So determinant of this FGH, okay, is also going to be continuous in S, okay, belonging to AB, okay, and FGH being orthonormal, implies that the determinant of FGH is always equal to plus or minus 1, okay, and so by the intermediate value, so I want to say by the intermediate value theorem, okay, either determinant FGH is plus 1 on all of AB, or determinant FGH is minus 1 on all of AB, okay, but at S naught it is plus 1, therefore it is plus 1 on all of AB, okay, but at S naught determinant of F S naught, G S naught, H S naught is actually determinant of I cap, J cap, K cap, which is actually determinant of the identity matrix. This is plus 1, okay. Therefore, this implies that determinant of FGH is equal to plus 1 on all of AB. And what does this imply? This implies that FGH is a right-handed orthonormal frame for all S. Okay. So once you have done this, you can be assured that this is really the orthonormal frame for a curve. Now, how do you get the curve? It's very simple. FGH should be the T cap, N cap, and B cap of the curve. So your F must be the T cap, but T cap is gamma dot. So gamma should be integral of gamma dot. So you have to integrate F to get the curve. Okay. So we just integrate F to get the curve and verify that that curve has capital phi as the curvature function and capital psi as the torsion function. So that's a straightforward verification. We can do that. So let's do it. It's kind of quite straightforward. Now we can define gamma of S to be, you see, how will you do this? So you see, you know what you do is gamma S minus gamma S naught is equal to integral from S naught to S gamma dot of S ds, okay. And I'll put this in quotes because this is just by hindsight, but your gamma dot is supposed to be your notice that gamma dot is going to be T cap gamma, and then you have N cap gamma, and then you have B cap gamma, and these three fellows are precisely your FG and H. So that is the frame, that is the Frenet-Serret frame. This is equal to FGH. Okay, so therefore you keep that in mind, okay, and therefore to get gamma dot is F, therefore gamma is integral F. So basically what you do is that you write this is equal to integral S naught to S Fs ds. So this is how your curve is defined, gamma S minus gamma S naught. So this is your curve for S belonging to AB. Okay, and the moment you define the curve like this, this is a unit speed curve. Why? Because by the fundamental theorem of calculus, if you differentiate, you will get d by ds of gamma S is equal to Fs. So this implies d by ds of gamma of S, which is gamma dot of S, is f of S, and notice f of S is a unit vector because it's part of a right-handed orthonormal frame. So this implies gamma is unit speed. Okay, so you've got a unit speed curve. All right, now it's a matter of calculation to show that for that curve, G is the principal normal, H is the binormal, okay, and then to show that capital phi is its curvature, the original capital phi that we started with, and capital psi is its torsion. That's a direct calculation which we can do. So we can just do that, and I think thankfully we will be done with the proof of this. So you see, yeah. So we have, gamma s minus gamma of s naught is equal to integral s naught to s fs ds. Okay, mind you, f is actually c1, so f is continuous, so its integral exists. And no, see this, of course this implies gamma dot of s is fs, and this gamma dot of s is by definition t cap gamma of s. Mind you, it's unit speed curve, right? And mind you, f is c1, so t is actually c1. Okay, you know that they all should be continuously differentiable, right? Now what about the curvature? What is k gamma of s? K gamma of s by definition is norm of gamma double dot of s. That is the definition. Okay, and but you see gamma dot is f, so this is just norm of d by ds of gamma dot of s. So this will become norm of d by ds of f of s. So I'll get norm of f dot of s. Okay, and but you see how are f, g and h, they were solutions of that Frenet-Serret. So you see f dot, g dot, h dot, so f, g, h satisfy this ODE, which is f dot, g dot, h dot is 0, phi of s 0, minus phi of s 0, psi of s, and then 0 minus psi of s 0, then I will get f, g, h. Okay, so so from that what you will get is that f dot is just phi g, so you will get norm of phi of s times g of s. Okay, and but you see norm, this scalar, when you take out of the norm you have to put a mod, so you will get mod phi s into norm g of s. Okay, but you see norm g of s is 1 because fgh is orthonormal frame, and the mod phi of s is actually phi s. That's because phi of s is given to be a positive function, so this is equal to phi of s. So you see the curvature of the curve is the given function phi of s. Okay, what about the principal normal? N cap gamma of s by definition is 1 by k gamma of s times t cap dot gamma of s. So this is the first Frenet-Serret relation. So if you do that, but this you can use the k gamma value, it is 1 by phi s. Okay, and t cap gamma is what? See, t cap gamma of s is actually your fs. Okay, so t cap dot gamma of s is going to be f dot of s. Okay, so this is going to be this times f dot of s. Okay, now again substitute the value of f dot of s is actually phi s into gs, so this is 1 by phi s into phi s into g of s, and you therefore get equal to g of s. Therefore you see g is the principal normal. Okay, then what about the binormal? See, b cap gamma of s is by definition t cap gamma of s cross n cap gamma of s. So this t cap is, we have just it is f dot s cross n cap gamma of s is g, sorry, not f dot, it's just fs cross gs. Okay, but you see fgh is an orthonormal frame, so f cross g is h, therefore this is equal to h of s. Okay. Then there's only one more thing that you have to verify, that the torsion is the function psi. That is also quite straightforward. Tau gamma of s is going to be tau gamma of s is by definition minus b cap gamma of s dot I think I should write dot n cap gamma b cap dot n cap gamma s. Okay, this is the torsion, all right. And so if you write it, this is going to be minus, see, the b gamma is h, so b cap dot will be h dot s dot n gamma of s is just what is n gamma? N gamma of s is gs. Okay, but you see this, what is h, this is minus, what is h dot? So look at this formula, h dot is minus psi times g. So I will get minus psi of s times g of s dot g of s. So I will get it will become psi of s into norm g of s squared, but g is orthonormal, so this is 1, so this is just psi of s. So you see the torsion is exactly psi, so you are done. Therefore you have managed to find for the given function functions capital phi of s, which is a positive C1 function, and this continuous function psi, you have found a curve for which these are the curvature and the torsion. And you already know that if you could have found another curve, okay, but the curve is fixed because of the following reason. If you find another curve with the same curvature and torsion, these two curves can be moved by rigid motion, but then these two curves, if you assume they pass through the same point, okay, then the translation component of the rigid motion is not there, and if at that point even their Frenet-Serret frames match, then they are one and the same curve. So there is only one such curve with the property that at the given point S0, the Frenet-Serret frame is exactly ijk. So this is a unique curve. Okay. So so you have found this curve uniquely. Yeah. So it's just hindsight. See, I find this fg. See, I find this I find this f, g, and h, which satisfy the Frenet-Serret differential equations with the given curvature and torsion functions. But you see, when I say Frenet-Serret differential equation, I am being very loose. I am not saying this is the Frenet-Serret differential equation of a curve that is already given. I have a differential equation for which which looks like a Frenet-Serret differential equation of a curve, for which in the place of the curvature function of the curve there is some function capital phi given to me, which is positive C1, and in the place of the torsion function there is a function capital psi given to me, which is a continuous function. And I am trying to, given that data, I am trying to show that there is a curve for which these are actually the curvature and torsion functions. So what I have to do is, if there is such a curve, each Frenet-Serret frame should satisfy this Frenet-Serret differential equation. So you first solve this Frenet-Serret differential equation, not knowing that it is the Frenet-Serret differential equation for some curve. You just solve the differential equation, you get solutions f, g, and h. Then what you do is that if this f, g, h has to come from a curve, then it should be right-handed orthonormal frame. Okay, or it can be a left-handed orthonormal frame. Okay, but therefore, but how did you get this f, g, h? You did not get it already from a curve. The curve is something that is like a ghost. We are trying to find that. You are only getting a solution of f, g, h for that differential equation, and therefore just because you got a solution for that differential equation, it is not necessary that that is going to be the Frenet-Serret frame for a curve. So I have to verify the necessary conditions that that is actually a properly handed orthonormal frame. So I verified that FGH is an orthonormal frame, and I verified that at one point you make it right-handed, then it is throughout right-handed. So what has happened is I still don't have the curve, but I have been able to get a right-handed orthonormal frame with the initial condition that at S0 it is the standard frame ijk. Now from such a frame you can get a curve. How will you do that? Had it been the orthonormal frame of a curve, then this f dot must be t cap gamma, which is gamma dot, and this g should be n cap gamma and h should be b cap gamma. So the clue is this f should be gamma dot. No, so the f should be gamma dot. Therefore, this gives you a way of saying that gamma can be recovered as integral of f. So that is the reason why I am defining, gamma like that. I am defining, see, if I am defining, keeping, so why I put this in quotes is that, you at the back of your mind, you think that had there been a curve, this will be true. But even though now there is no such curve, you can always define it by this method. So you define gamma like this. Then it is a matter of verification now that we did that this gamma is unit speed, then the principal normal is given by g, the binormal is given by h, and the curvature function is capital phi and the torsion function is capital psi. It's a matter of routine calculation. You understand? So you have to verify. See, if this FGH was the orthonormal frame of some gamma, if we are going, see, you are just trying to do a kind of back calculation. You are making a back calculation. You are trying to say that there is a gamma for which this t cap gamma, n cap gamma, b cap gamma are exactly f, g and h. But what you do is that from where can you get gamma directly? From the t cap gamma, because t cap gamma is gamma dot. So if the t cap gamma, which is gamma dot, is f, so gamma dot is f, therefore gamma should be integral of f. So you can get gamma from f. So you define the gamma like this. Then you have to verify the compatibility. You have to show that for that gamma, the n cap gamma is actually g, and for that gamma, the b cap gamma, the binormal, is actually h, and for that gamma again you have to check that its curvature is exactly the function capital phi originally prescribed, and its torsion is exactly the function capital psi that is originally prescribed. All these things automatically follow if you just make one observation that gamma dot should be f, so gamma should be integral f. That's how you recover gamma. So what this tells you is that you give me any right-handed orthonormal frame, okay, I can always integrate the first member to get a curve, that's all. And the curve will be unique if you fix a point through which it has to pass, and also fix the orthonormal frame at that point. That's all, finished. They satisfy this differential equation. The torsion is also given by capital psi. See, it's the point is that at the back of your mind, you imagine that there is really a curve, okay, but don't use it. You use it only at one point, namely at this point. Once you have verified Fg is right-handed orthonormal frame, how do you get gamma? Gamma dot should be f, therefore gamma should be integral of f. That defines gamma for you. And once you define that gamma, you verify everything else falls in place. You understand? That is the idea of the proof. See, understand there is this logic. You start with a curve, unit speed, then you take its Frenet-Serret frame. They satisfy the Frenet-Serret differential equations, right? So these are implications. I have a curve. If I have a curve, I have the Frenet-Serret frame, and the Frenet-Serret frame satisfies the Frenet-Serret differential equation, right? Now the Frenet-Serret frame is not just any solution of that differential equation. It is an orthonormal frame which satisfies the differential equation. Now what I am doing is I am doing the reverse. I am starting with the differential equation. In that differential equation, only the curvature and torsion functions are predetermined. They are already given to me. What does the theory of differential equations say? It says that I can find a solution for that. So I take one solution FGH. Now it's my job to verify that this FGH actually are the Frenet-Serret frame for some gamma. There is no gamma. So what? So if they have to form a Frenet-Serret frame, then first of all they must be orthonormal. Because you see, when I solve the differential equation, I only get a solution. Nothing directly says that that solution is an orthonormal frame. Mind you, I want to point out, this is after all a homogeneous differential equation. There is always a trivial solution. If I put 0, 0, 0, 0, 0, 0 on the derivatives, it will always work. Always the trivial homogeneous solution is there. That is also a solution of your Frenet-Serret differential equation. That is of no use because they are all zero vectors. How can they be an orthonormal frame? So you are taking a non-trivial solution, and to make sure that it is not the zero solution, you should be careful. At least at one point you make sure that you are giving some initial condition, namely that's why at the point S0 you fix the frame to be some known frame I cap, j cap, k cap. So you have now this FGH which solve this differential equation. Your job is to show that this comes from a curve. First of all, you have to therefore show it is necessary. You have to show that this is actually orthonormal. So we proved the orthonormality. Then we also showed that because everything came from the initial conditions. That's what you have to appreciate. And the fact that the Frenet-Serret differential equation is first order linear. Okay. Then we proved that it is also right-handed. Now you have sufficient power to get the curve. Now had it come from a curve, then that gamma dot should be the first member f. So that gives the clue that gamma will come by integrating f. So use that idea and define gamma like this. And then you verify that for that gamma, the n gamma and the n cap gamma and b cap gamma are exactly g and h. And its curvature function is capital phi and its torsion function is capital psi. So it's a matter of everything will fall in place. You just have to use the Frenet-Serret, the differential equation that this solution satisfies. So that is the sequence of verifications that you do. Okay. No, so that what finally remains is every curve gives rise to a orthonormal let us say every right-handed curve gives rise to a right-handed orthonormal frame. Conversely, every right-handed orthonormal frame comes from a curve. That needs to be proved. Okay, that needs to be proved. Okay, and but the point is that this right-handed orthonormal frame cannot be an arbitrary right-handed orthonormal frame. It should satisfy the Frenet-Serret differential equation. Therefore, in the places of the usual curvature and torsion, some functions must be there. It has to satisfy such a differential equation. Okay, that is also important. All right. So you take such a right-handed orthonormal frame which satisfies something that looks like the Frenet-Serret differential equation with the some function instead of the curvature function and some function instead of the torsion function. Then you can fit a curve to that frame, right? Then you can fit a curve for a space curve to that frame. That's what we verified. I mean, I'm saying that it more or less seems natural and obvious, but the point is you have to write down the proof and really nail it down. I mean, it's just getting the a kind of positive feeling that this is going to be true. That's not enough for math. You need to write down the proof and till the last dot you have to write down everything. Okay, that's what we are doing. Okay, so so incidentally I wanted to say that there is also a classification theorem for plane curves, but that will involve signed curvature, and the problem is that that cannot be deduced from this classification theorem. The reason is because there is a sign in the curvature, and if you take a left-handed circle and a right-handed circle, they are not rigid motion equivalent on the plane, but in space they are rigid motion equivalent by a rotation. Therefore, the problem is that you cannot get the classification theorem for plane curves as a special case of the classification theorem for space curves, and therefore I will also quickly tell you next time how to get the classification theorem for plane curves, because there the Frenet-Serret differential equation will involve signed curvature, and we will have to importantly use the fact that there is a turning angle for a C1 unit vector. That is going to be the key. Okay, so we will prove that also. Okay, so I think I will stop here. Okay, thank you for your patience.